Welcome back to the second segment on key distribution. So to recap a little bit, we spent quite a while studying how you can build cryptographic primitives that, with the aid of lots of nice mathematics, provide privacy and integrity of data, assuming you have appropriate keys for the parties that use them. And what we're now coming to is how do these parties actually acquire and come into possession of these keys? And we're seeing that it isn't trivial. There are various security risks and goals associated to them. We first looked at the asymmetric setting, meaning we tried to see how Alice can come into secure possession of Bob's public key in a way that guarantees that when she has a public key pertaining to be Bob's, it really is his. And that was done through the public key infrastructure and certificates and certificate authorities. And this is one central component of how the internet security infrastructure works. The second element, though, is that even prior to the asymmetric setting, we studied the simpler, more basic symmetric setting where Alice and Bob share a key. In that case, they both have the same key, and it's used for both encryption and decryption, and correspondingly for message authentication and verification of the tags. So here, E could be something like CBC mode encryption with AES to generate a ciphertext under key K, which Alice can decrypt if she has the corresponding key. Or Alice could generate a tag, say using HMAC with K, and then given the message and signature, Bob could verify the tag because he has the same key. But how do they get that key is the question we want to ask. Now, you might think we've already answered that. After all, we had this lovely Diffie-Hellman key exchange protocol whose ability was exactly to allow Alice and Bob, who never met, to come into possession of a shared key. So recall that we do it by fixing a public group of some order m. It's cyclic, would generate a little g. And once you fix that, Alex picks a random exponent, raises g to that power, sends that over, and along with that sends them something saying, hi, I'm Alice, here's my big X value. Bob will correspondingly generate little y and then big Y from it, and he'll say, hi, I'm Bob, and here's my big Y value. And now the math gives us a shared key. It's g to the power of the product of the two secret exponents, and you arrive at it by either raising big Y to the little x for Alice or big X to the little y for Bob. And that's great. And we agreed that this was effectively secure, so this ought to solve our problem. Once they have the shared key, they can perform all the usual symmetric crypto we want, like using AES modes of operation for encryption and decryption. But when you examine the security properties of this protocol, we see that what we established or agreed that it provides is security in the face of what's called a passive attack. It says that an eavesdropping adversary can't figure out the key. Eavesdropping means it learns big X and big Y by observing this communication. And then it tries to figure out g to the power little x little y, and due to the assumed hardness of computational Diffie-Hellman, it'll have a hard time. And that's, to the best of our understanding, that's true and all good. The difficulty is that when you want to start and initiate a communication with someone, you have to also establish authenticity. So the Diffie-Hellman key exchange in particular is subject to the same sort of entity in the middle attack that we discussed earlier. What happens is that the adversary Eve performs exactly the correct mathematical steps, generates big X exactly as Alice would and sends it to Bob. The only difference is she puts here a claim saying, hi, I'm Alice, which isn't true. And now Bob responds and sends to that person his big Y value and his name. The protocol is exactly correct as before, so they will generate their shared key, g to the power little x little y. Now Bob can start encrypting, The difficulty is that Bob thinks he's encrypting to Alice and she's decrypting, but Alice hasn't even entered this picture. She's nowhere to be found. She doesn't even know this exchange has happened. And instead, the adversary decrypts because it just has the key. So it's very easy then for some entity to step in the middle in this way and completely impersonate Alice. And this is the problem that we want to avoid. And this is technically called the insecurity of Diffie-Hellman against active attack. Now, before we think from this that Diffie-Hellman is kind of a useless protocol, looking forward, we'll see very much the opposite. What we'll see is that we eventually will find ways to add integrity, and having done that, it will be useful within them to actually run the Diffie-Hellman key exchange, and that's actually what happens in TLS. So it's what you're seeing happening in your usage. But let's go back to the basic question. So what we want is that in the presence of an active adversary who could get in the middle and send flows and claim that it's Alice, how is it possible for Alice and Bob to start from scratch, meaning they've never met and have no secrets in common, even though they may agree on public information like a group and a generator as in Diffie-Hellman key exchange, but then get a joint common key unknown to the adversary? And the answer is that it's actually mathematically possible to show that this is not possible. Effectively, this meet in the middle attack always works. The adversary can always impersonate Alice because Bob simply has no way or no information to distinguish Alice from the adversary. So realizing that, we see that if we want to solve this problem, we need something to get off the ground. We can't start from scratch as indicated here. We'll have to start with some information, something that gives these honest parties an information advantage over the adversary, something that Bob can use to authenticate Alice or vice versa. And we often call those things long-lived keys. There are many forms they can take. One of them is that we bootstrap to the public key setting. We assume that the parties have each other's public keys and are convinced of their authenticity. We do this because, for one thing, we know how to get there. That's what the public key infrastructure is supposed to do. In some cases, we have parties who already share a key and want to get another key, and that's another instance of the problem. And a third setting is that there is a trusted server and each party has a key with the server, but then the two parties want to get a key with each other. And so there's a three-party protocol to make it happen. And these are all different examples of this kind of long-lived information, which has to be itself established in some way, which is usually out-of-band or through other combinations of cryptographic and out-of-band material methods like the public key infrastructure. So the problem of exchanging a key so that Alice and Bob are in possession of a joint key in practice shows up as what's called session key exchange. And this is in some ways the real practical problem. What it covers is the fact that Alice and Bob are typically engaging in multiple communication sessions. So typically Bob is a server and Alice is a client, and you're conducting a Gmail session or or any such thing. And with a particular entity like google.com, you as a client will have multiple sessions. You will log in many times across many days, but also possibly all at the same time, just in different tabs in your browser, to have communication sessions. And the goal is that each of these sessions should be secured by a session-specific key. This key should be authenticated based on the long-lived information or keys, but different sessions should have fresh and different keys that have nothing to do with each other. And the actual encryption and authentication of data inside a session happens under that session's key. This is how the internet runs now. This is how communication is set up, in particular in TLS. One may ask, why do this? After all, you could directly maybe use public keys to perform all the privacy and integrity operations on the data, and we know how to set them up. But that would be, on the one hand, quite costly. Symmetric crypto is way faster than asymmetric crypto. But even more importantly, are various security attributes associated to sessions, and in particular the fact that we want to keep these sessions independent of each other. So if a session key in one session is compromised, it shouldn't compromise security of the other. And this is a very real problem which reflects not just compromise, but just the fact that different sessions could use keys in very different ways, such that an individual use is secure, but then when you look across multiple sessions, it's not. So in any case, this is what goes on. Session key distribution is really an interesting technical and problem, and also interesting historically. There have been many protocols over time given for this. Also, even though when you look at these protocols, they look fairly simple, usually like 3 or 4 rounds of exchange and a few encryptions and signatures. They're very hard to analyze, in particular because by now there are lots and lots of different security requirements imposed on them. History has shown a lot of attacks and broken protocols. And on the other hand, we need these things. They're used in TLS, SSH, many places at this point. So of the 3 settings we discussed, I will try to exemplify a little bit about the one where the long-lived keys are public keys. So I'm assuming that A has B's public key and B has A's public key, and these have been established, for example, through certificates and PKI and are trusted. And that's because this is the kind of protocol currently used in many places, with the caveat that in TLS, most often it's one-sided. Alice has Bob's public key because Bob is a server who has communicated his certificate to Alice, but Alice doesn't actually have a public key, and so Bob doesn't have that. But this also arises, sometimes it's also mutual, so we will stick with that for simplicity. So we could spend an entire quarter on this topic, and instead I'm just going to illustrate a few protocols. Now, for most of the crypto we've studied so far, we've been quite meticulous about giving game-based definitions of security and being very clear about the formal meaning of our security metrics and things like that. And we're not going to do that here. Instead, I'll just show you some protocols and we'll just try to eyeball them and get some intuition about what they might be doing. So this is a typical sort of scenario. What happens is Alice starts the protocol. She says, "Hi, I'm Alice." She sends her identity, and then she sends a nonce. So what is a nonce? It's just a random number of some sufficient length. And why does she send this? Because she's trying to make this session unique. This nonce will be bound into the key generated in the session and effectively be a way to make that key independent of keys in any other session. So Bob gets this information and then he sends back stuff. So what does he send? First off, in this protocol, Bob will simply generate the session key. So his job is to pick this key K at random, and then he wants to communicate it to Alice. Obviously, he can't send it in the clear, but Alice has a public key, which he's in possession of, which means she could decrypt anything encrypted under this public key. This denotes encryption under Alice's public key. It is decryptable by Alice using a secret key. He performs that encryption, which may be randomized to get a ciphertext, and he sends that ciphertext over. When Alice receives that, she can do this decryption with her secret key and recover the session key, and now they have a joint session key. So at some level, the protocol has accomplished its purpose of distributing a key just by communicating this ciphertext here. But there's a lot more to it, because if you just do that, there's no authenticity, no freshness, nothing like that. So Bob does a bunch of additional stuff. He also picks a nonce, a fresh random number, so that he's also tying something into the freshness of the session. He puts his identity here, and then he authenticates everything he sent, meaning he authenticates the flow which contains the ciphertext, both nonces to tie it to the ciphertext, and both identities. What does it mean to authenticate? Well, Bob has a secret key whose corresponding public key is possessed by Alice. So Bob can sign. This means Bob's signature in this case of the message in here, which is all this at this point, under his secret key, and it is verifiable by Alice, who has this corresponding public key. So now when Alice gets this flow, she first checks the signature. If it's invalid, she stops the protocol. And only if it's valid will she decrypt the ciphertext C here to get back K. Okay, so now at this point, Alice has K and Bob has K. So you would think, we're done, we have a session key. But there's a final step in which Alice effectively confirms this by sending her identity and a signature of the nonces and identities together. And this is effectively saying, I'm speaking about the protocol instance given by these two nonces. That way I tie it into what you sent before, and I'm acknowledging that I've got the information properly and I've accepted it. This signature is under Alice's secret key, verified by Bob under his public key, and if he fails to verify here, he'll reject. Now this is a very high-level description of the protocol, and of course it doesn't get into what are the different security properties. There's a whole slew of them, freshness and security under what are called session key reveal attacks and all kinds of things. So rather than get into that, we'll actually go a little further. It turns out that nowadays modern session key exchange protocols want to enhance the type of things we just saw to incorporate other features. And one of the important ones is what's called forward security. The threat here is that the adversary has somehow compromised your system through malware or phishing or whatever, and it has obtained your long-lived secret keys. So remember, Alice and Bob have public keys and they store the corresponding secret keys. Those are long-lived. They remain across many, many session key distribution protocol instances. And if those are compromised, we want things to go bad as little as possible, which we'll see what that means. There are many other concerns. For protocols used in mobile settings, we want sometimes that eavesdroppers can't figure out who are the entities communicating. They might typically know the server, but they shouldn't figure out who the client is. There are other settings as well. One of them is the setting of passwords. So remember, a password is simply a key that you memorize. And the security difficulty with passwords is a tendency of users to not make them unpredictable or random enough. We pick them from a relatively small predictable set. In other words, attackers are capable of following a set of candidate passwords, and they call that a dictionary. And if your target password happens to fall in their dictionary, they would be able to recover it by searching across all passwords in the dictionary. And that's called a dictionary attack. The difficulty is that users often pick their passwords in such a way that they do fall in the dictionary. How does this attack work? It assumes that the attacker knows some image of your password under some public function. There's some function that it can itself compute, like a hash function, and the adversary has this hash result. Once that's the case, it can easily find your password if it lies in the dictionary by trying every dictionary password, and for each of them it will compute f on that and see if it gets back the target, and if so, this input here is likely to be your password. So this concern also comes into session key exchange, in particular because of these poor choices of passwords. So passwords are prevalent. Despite the presence of strong crypto, a lot of the crypto we do is ultimately based on keys derived from passwords, and we use passwords all over the place. So preventing these dictionary attacks is quite important. Now, to think a little bit further about that, many times now if you go to a website and try to create your password, they will give you rules, 8 characters, some uppercase, some lowercase, and so forth. And so if you enforce things in that way, of course, you have a much better chance of getting passwords that don't fall in the dictionary. But unfortunately, it's still the case that there are many poor choices, and moreover, attackers are getting better and better at building dictionaries. And little tricks that you might use are not going to evade these dictionaries. You can look, for example, at the list of most popular passwords which you can find on the internet. You see, for example, that the word password in 2011 was the top ranked password. By 2013, it was 1, 2, 3, 4, 5, 6, and so on. So if these are the kind of passwords people are picking, then clearly there will be a lot of dictionary attacks. So how does this all tie back into our topic of session key exchange? We are looking here for a key exchange protocol where Alice and Bob start with a shared password. And what they're looking for, however, is that they end up with a cryptographic session key, like an AES key, but in such a way that the adversary cannot mount a dictionary attack on it. And it's quite interesting and not necessarily trivial to do this, because what you need to ensure is that no public function of the password is ever visible through the protocol. And making that possible requires a fair amount of trickery. So I haven't looked at a lot of details. I haven't shown you a lot of the example protocols and so forth, but we've just gone through a high-level overview of this area. We can look a little bit now going back as to how all this is reflected in TLS. So this picture shows the TLS key exchange and communication. So TLS starts out with something called a client hello and an exchange of cryptographic information, and then further such things, they call them SSL, but it's TLS. Further such things from the certificate cipher suite is a choice of algorithms to use, things like that. And here you see a key exchange. And this key exchange is where the session key exchange protocols we studied would be used. And prior to this, you have certificates being sent by the server as to establish the authenticity of the public key that's used in the key exchange. Once all of this is done, the message exchange is encrypted and also authenticated, although they don't say that, with the key that you got from the key exchange. If you want details of TLS, there's a really nice website here called Illustrated TLS Connection, which really goes into details. You can click on any flow and it tells you exactly what's in the flow. So this is the client hello. The client begins with all this. Then there's a server hello. The server provides things like the selected protocol version, some random data, session ID, cipher suite, that just means what algorithms it supports, and so on. Then there's server certificate, right? So this is where the CA provided certificate that the server has is communicated to the client, and it includes the host name or URL of the server and the server's public key. And this proof from the trusted third party is effectively the certificate, the signature and the certificate. Following that, there's a key generation, and this is the session key exchange protocol, and it'll have a few steps, the server part of it, client part of it, and so forth. And then there'll be some sort of termination of that, and then there'll be a client key exchange generation for it, it's part of it. And based on that, they'll calculate session keys. And once they have those session keys, and then the protocol is over and you can move to start encrypting. We could also spend a long time studying TLS. One of the interesting aspects of it is that by now we have covered quite a bit of the crypto that's used in TLS, at least in the sense that we've looked at the goals and principle. TLS uses authenticated encryption, which we've studied how to do. It uses session key exchange, which we just looked at. It uses certificates. Authenticated encryption itself uses MACs and encryption and all other stuff we studied. All those are done with block ciphers and so forth. But the actual TLS protocol has historically been vulnerable to many different interesting attacks. And it's interesting to go through them. You'll find that some of them are due to crypto weaknesses, many are not. And it's really a nice illustration of the interaction between real world settings and kind of the abstract crypto we look at.